How's it going? Back in 1 second. I go grab something from my office. Cool. All right, it's 12:30. 12:30. Let's get started. Yeah. All right, Lord, thank you for bringing us together this afternoon. Thank you for the promise of the weekend coming up. Pray that you would help us to focus, get everything done that we need to get done. Strive in this hybrid learning environment. Help us to stay focused, right? Help us to have a great weekend. In your name we pray. Amen. Okay, so there, we'll just use this one. Seem to have lost or misplaced. Let's say misplaced. It sounds less, I guess, forgetful. Um, my clicker. So I'm gonna have to stay pretty close to the podium today. All right. So what are we doing today, right? Well, first, let's take a look at this. What was going on last class, right? Understand equations, no plotting stuff. I'm confused by this. I don't know what plotting, what we're talking about plotting. Maybe we got hacked. Who knows?
I felt that on this like I understand some of like what was going on and all those. I just like when I it's not like how you would figure out how to do that.
Okay, gotcha. Okay, we'll slow it down. All right, we'll slow it down then a little bit when we're doing problems. Make sure that we're all good, like step by step, right? If you don't understand a step, make sure you stop me, right? And we'll talk about it. Okay. You guys got anything else you want to talk about? Anything else that was that's on your mind from last class? Well, no. Okay. All right. So homework 2 and the 2 Learn Smarts due on Sunday. Please do them. Please do them. Let's see. Today we're going to continue with what we were talking about last class. Right? We're going to continue on with impulse. We're just trying to build our toolbox right now, right? We're going to talk about impulse. We're going to talk about momentum because of that, because impulse and momentum go hand in hand. When we talk about impulse, we're talking about really collisions, right? So how do we deal with two particles that are hitting each other, right? Which leads us right into impact, right? Then we're going to jump into topic 3, which it says kinetic energy. Well, didn't we already kind of talk about kinetic energy? Yes, we did. We'll get back into this. We're going to start talking about systems of particles. All right, so what if I have more than one particle that are moving together, right? So they're linked in some way. How do we talk about them? So what's impulse? The easiest way to envision impulse, right, is a hammer hitting a nail. It is a very large amount of force that lasts for a very, very short time, right? It's an impulse. It's there and then it's gone, right? So the thrust of a rocket acts over a specific amount of time to give us some linear momentum. The impulse applied to a rail car by the wall brings the momentum to 0, right? This is a particularly useful thing to know about when we're talking about things that are colliding, right? So we're talking about collision because we can determine, velocity before and after collision from this and which way two objects will go after they collide. Right? There's a lot that we can do here. So we're going to go through some derivation, and I'm probably not going to spend a lot of time on this because, again, it's nice to know where it comes from, but we're really just concerned about what the end goal is here, right? So imagine for a second I've got some particle here, right? And it has some momentum to start off with. It's moving, so it's got some momentum, right? M times V, momentum. So it's moving, so it's got some linear momentum, right? We can say that the initial momentum plus the sum of all of my impulses between state 1 and 2 is equal to my final momentum, right? That's what we can say here. All right, so that's great, right? But what is it? Well, what is an impulse? Well, looks like it's the integral of a force with respect to time, right? And that's true. We're going to write it a little bit differently, though, and we'll talk about it in a second. Dimensions of an impulse are force times time, right? So we've got Newton seconds, right? Newton seconds or pound seconds. That's what we're going to be working with in terms of units of impulse. Impulse problems are very useful when we need to find the amount of time that something takes to happen, but we're only given a force, right? That's what, that's when they're useful. We'll go over that more in a little while, right? So again, the final momentum of a particle can be found by adding the initial momentum and the impulse, right? So if you have an impulse and this, you add these two together, well, your final momentum is right here, okay? So remember, when we add vectors, you put them tip to tail, right? Put them tip to tail. Okay. So we're going to start wanting to draw an impulse momentum diagram when we do impulse momentum problems, okay? Why? Because this is a graphical representation of the equation that we're going to use, okay? So I've got a force acting on a particle during a very short time interval, and it's large enough to cause a significant change in the momentum, and that's what we define as an impulse force, right? So it's a large force over a very short period of time. Remember, hammer hitting a nail, right? You smack it, that force is strong for a brief second, but then it's gone. If you're the nail, you get bopped on the head, right? It sucks, but it's only there for a second, right? Less than. When impulsive forces act on a particle, we can write our equation as if this is the, as Dwight Schrute would say, right? These are the money beats right here, okay? These are the money beats, okay? This is the equation that you want. That equation comes directly from this diagram. Just like when we have a free body diagram, right? We can write Newton's second law. Well, when you have an impulse momentum diagram, we can write our impulse momentum equation, right? So what is it? It's the initial momentum that we have as drawn as by a vector, right? Plus the sum of my forces times the change in time, right? Plus the sum of my forces times the change in time. And that's equal to the final amount of momentum that I have. Notice in this, the weight of the ball, the impulse, due to the weight, is considered to be zero, right? Is that always going to be the case? No. Why is it in this case? Well, in a lot of impact problems, the force of the bat hitting the ball is significantly stronger than the force of the weight over time, right? And so we'll just neglect it because it's not going to make that big of a difference. Right? That's what this says. When a baseball is struck by a bat, the contact occurs over a short time interval, but the force is large enough to change the way the ball is moving, right? So when you pitch it, it comes in, and it goes out the other way. You reverse the direction of motion. Non-impulsive forces are forces for which F times delta T is small and therefore may be neglected, like the weight, right? So when compared to the force of the bat hitting the ball, the weight is small, and so we typically neglect it. Is that right or is it wrong? It depends, right? Depends on what the weight is, depends on what your time interval is, right? Never wrong to include this. We will do a problem where we do include it, and you'll see it's pretty much exactly the same answer. It changes very little, so that's why we end up, so we'll basically prove it, right? We'll prove why we ignore this. Right?
So on that diagram, the baseball point this way, and the force bats point this way.
Right. So think about what happens, right? The ball's momentum is coming towards the batter, right? And the batter applies a force in the opposite direction of the momentum, right? So the impulse force is acting, in this case, would be acting opposite of the momentum. And then in the final case, we've changed the direction of the ball, right? It's going the other way. So a lot of the times what you'll see is for collisions specifically, right? you need a strong enough impulse to either stop your momentum completely, like in the case with the sled hitting the wall that we talked about right in the first slide, or you need something even stronger than that to have it change direction, right? Because I mean, if you're going one direction, you have to think of it this way, just in terms of the velocity. I've got to slow it down, and then I've got to increase the velocity in the opposite direction, right? That's a lot of, it's going to take a lot of work. It's going to take a lot of work. All right, so this is what we're striving for, right? These diagrams here, these are our impulse momentum diagrams, right? We will draw the impulse to start with, plus the sum of my impulses, right, which are just my forces times delta t, times the time interval that we're interested in, and that's going to equal my final momentum. Well, Dr. D, in physics 1, they only told us about conservation of momentum. I thought momentum was always conserved. Not always conserved. It can be conserved. If momentum is conserved, what does that mean? That means that the momentum that we have at the beginning is equal to the momentum that we have at the end. In order for momentum to be conserved, this has to be 0, right? If this middle one, if there's no impulsive forces acting on our body, then our momentum is conserved. Well, when would that happen? It happens actually quite a bit, okay? And we'll talk about that in a little while. But first, let's just try one. Let's try this. We'll do this one together here. Let's see what's going on. Grab my notes right here. So, you probably noticed this in the textbook. There's a lot of there are a lot of sports analogy problems, specifically track and field. All right, so I've got a long jumper, right, and he's sprinting. Right, so the jumper approaches the takeoff line from the left with a horizontal velocity of 10 meters per second. It remains in contact with the ground for 0.18 seconds, takes off at an angle of 50 degrees with a velocity of 12 meters per second. We want to determine the average impulsive force exerted by the ground on his foot. So how much is the ground reacting to his foot, right? He slams his foot down, and there's some force of the ground pushing back up on him, right? Called the normal force, right? We want to give our answer in terms of the weight of the athlete. So we don't know the weight of the athlete, right? We don't know how much he weighs or what his mass is. So the first thing that we need is our impulse momentum diagram, right? So let's talk about that. Right? So what would you say? Well, how would you characterize the momentum of the linear momentum of this jumper to start with? How would we start that? How would we discuss that to start? What is momentum, right? The mass times the initial velocity, right? So keep it in terms of variables to start with. Don't plug any numbers in to start, right? We want to do everything symbolically, because potentially we could reuse all of our work for different numbers, right, if we do that. So what's his momentum to start with? Isn't it just mv initial pointed to the right because that's the way that the velocity is going? So you've got m times v naught, right? I know what you're thinking. You too can learn to draw just as well. I promise. My 3-year-old's almost there. He is. He's almost there. He's a raw talent, right? A raw talent. All right. So I've got my stick figure guy here, right? And he's going. Then I've got my impulses. Notice what I've done here is I've eliminated the ground, right? It's kind of like a free body diagram. I've isolated the body of interest here, and I'm drawing the forces that are acting on the jumper. I've got his weight times delta t, and I've got the average force on his foot. Now, why is it the average force? Well, because his entire foot is touching the ground, right? So potentially there is a different force at each point where he's making contact with the ground. It might not be perfectly flat, it might be bumpy, right? So we're just going to call this the average force. We're going to localize it as one force acting directly on the foot pad times delta t. All right, is everybody okay with the first part of this, right? It's just momentum, m times v, and our impulses. Is everybody all right? Have any questions so far? Yeah, love it.
It's mostly just out of curiosity. Why is momentum going to be?
Okay.
I thought that was an F, and so it would be.
No, oh yeah. My handwriting strikes again. Okay. So all of that is equal to my final momentum, right? And we know that he's going to be moving at 50 degrees, right? We have some momentum that's 50 degrees from horizontal in that direction. Okay. What were we told here? We were told that V naught was 10 meters per second, right? So we want to write down our knowns. We know that delta t is equal to 0.18 seconds. And we know that V sub f is equal to 12 meters per second at an angle of 50 degrees, which we have drawn there. We'll hold those off to the side. We'll save them for later. Okay. So that's great. So remember, momentum is a vector quantity, right? Momentum is a vector quantity, and because it's a vector, what does that mean? Well, that means we should be able to break this into x and y components up here, right? I'd have an x component in my velocity and a y component in my velocity, which would be scaled by my mass. Right. So let's talk about this in components, right? Because momentum and impulse are vectors, right? We said we can break them into x and y components, right? So let's talk about the x direction, momentum, and impulse. Right? All right, so initially at state one, right? So when I say state one, I mean this, and state two will be the final states, right? So initially, how much momentum do I have in the x direction? Not the number, just how much of this? What percentage of this? Yeah, it's all horizontal, right? It's all in the x direction. So my initial momentum in the x direction is mv naught, right? What about impulses? What do I have as impulses? Well, I can break this f average into x and y components too, but I don't know the angle, right? So what I'll write this as, if we were to break this into components, right, it would look like that. X going to the left, y going up. You have negative f average in the x direction times delta t. And that's the only impulse acting in the x direction, right? And what is this going to equal? Well, it's going to equal the x component of my final velocity, right? Or my final momentum. How do I get the x component here on this? There it is. Cosine of 50. But remember, the problem statement asks us for what? It asks us to do this in terms of the jumper's weight, right? So we're going to need to figure out the weight from the mass. How do we do that? How do I change mass into something that's related to weight? What's the definition of weight? Mass times gravity, right? So we divide by gravity. We have that equation that I wrote up there on the top right corner. Mass is equal to weight divided by gravity. And so we can rewrite this as weight divided by gravity times V naught minus F average in the x direction, delta T, is equal to the weight divided by gravity, V sub F, cosine of 50 degrees. Right now, we can plug in some numbers here, right? Well, you know what? We'll wait till the next slide to do the numbers. We'll leave that as is for a second. Leave that as is for a second. Now we're going to talk about the y direction. So in the y direction, right here. We'll call that 1. All right, the y direction. What's my initial momentum in the y direction? 0. What's my y direction impulses?
0 plus force average,
Yes. So because they asked us to do this in terms of the weight, we're not going to ignore the weight here. I know it's confusing. When do we ignore it and when don't we, right? So typically something small like a baseball will ignore the weight, but for a human, we're not going to, right? Olympic athlete is going to be, Olympic long jumper is going to be what, like probably 180 to 200 pounds, typically. That's going to be a significant amount of impulse that they're imparting due to their weight, right? So we're going to keep it in this scenario. So this is going to be F minus W times delta T. Remember, the delta T is not changing, right? So we've got two forces multiplied by delta T here. Two forces. And then we need the Y component, right, of this. And I'll just go ahead and I'll write it as W over G, V sub F, sine of 50 degrees. All right, so we've got these two equations. Technically, we've got 3 unknowns, right? But we wanted this in terms of the jumper's weight, right? So we're good, right? What we're going to do is we're going to plug in some numbers now, right? So we're going to plug in all the things that we know. We'll do that on this next slide where there's room. So if I plug in everything that I know for that first equation, right? What do I end up with? Well, we got 10 times the weight divided by gravity minus 0.18 F average in the x direction is equal to 12 times cosine of 50 degrees times the weight divided by gravity. All right, so that's my x direction equation. Here's my y direction equation, right? When I plug everything in, I will get F average in the y minus the weight is 0.18 is equal to the weight divided by gravity of 12 sine 50 degrees. Yeah. That's just plugging in what we know, right? So now, what can we do? We can solve each one for F average. We can solve each one of these for F average in the x direction and F average in the y direction. And then we'll know that y and the x components of our forces as a function of the weight, and then we're done with the problem, right? So let's solve this one for F average. I was going to solve this for F average in the x direction. What do I've got? Well, I've got to move a bunch of stuff over, right? So I'll end up with 10 minus 12 cosine 50 degrees divided by 9.81, which is gravity, times 0.18. That whole thing times the weight. I can likewise solve this for F average in the y. And I'll get W plus 12 sine 50 divided by 9.81 times 0.18 times W. Okay. Everybody good with me so far here? Why are we doing this, right? Why? We were asked specifically to find the average force that the ground is exerting back on the jumper, right? In terms of the weight of the jumper. So what if I wanted to write this as one complete vector, right? For force, because it seems like a good idea for just F average. Well, I can write this as F average x in the I direction plus F average y in the j direction, right? So it would just be 10 minus 12 cosine 50 degrees divided by 9.81 is 0.18. That's a weight in the I direction. So rather than write all that out, let's do it this way. This whole thing right here, right? That whole thing, if you do the math out, what do you get? Negative 1.295 times W. If I do the math on this, what do I end up getting? You end up getting 6.21 W times W. So what is this telling us, right? What is this telling us? This is telling us that the force is going to be pushing back to the left and up, right? So the force exerted by the ground is pushing against the jumper. It also tells us that the force that the jumper, that the ground exerts on the jumper is a function of the jumper's weight, right? So the heavier that the person is, the more force the ground will exert back, which makes sense because it's really just talking about normal force, right? But notice it is a resistive force, right? So the heavier that we are, this is going to be pushing the jumper back. But you want to be going that way, right? So there's interesting mechanics at play here. I know that one's a little bit abstract, right? We're doing things in terms of the weight. Okay, but that's one of the, that's one application of this, but I think the more relevant one comes up when we talk about collisions, right? Collisions of particles, collisions of rigid bodies. We'll cover that later, but collisions is something that we can get into now. You guys have any questions on this? Is that all right?
Is this like solved over with
Yeah, because we don't know the weight. So I'll keep saying this throughout the semester, right? One of the big advantages of doing things symbolically is that now I have a mathematical model that's good for any situation, right? So you can tell me the weight of that long jumper, and under these conditions, I can tell you what the force is, right? Which is more powerful and less of a headache. Say like, I don't know if you're doing the homework, right, and you mess it up 3 times, so you have to submit it and get a new attempt, right, and then it gives you a new number. And instead of you doing the whole problem all the way through again because you put numbers in at the beginning, it's literally just plug some numbers in your final step and test it out again. Right? Yeah. But yes, this would be, if you left it as, if you had it here, it'd be all the way solved. I'd be happy if you had the X and Y components as well, all right? All right. Any other questions? No? You guys hear me okay? I'm very self-conscious about it. My other classes tell me that they can't hear me, but this room doesn't have as much HVAC noise as the other one that I teach in. So I guess that's positive. Although it does smell like gas leak in here sometimes. So I guess trade-offs, right? Trade-offs. All right, let's talk about impact, right? So this, I think impact is infinitely more interesting than the problem that we just did, right? And why? Why would I say that? Well, it's talking about when things collide, right? So this allows us to do so much more, right? We can start talking about pool ball problems. We can start talking about bullet and block problems, right? A lot of cool problems, right? So let's define what is an impact, right? What is it? Well, it's a collision between two bodies which occurs during a small time interval. That sounds kind of like an impulse, right? It's a force. A collision is something that happens over a small time interval. Okay, cool. We can define things like line of impact, right? So the line of impact is a line that connects the center of both particles that are it's a line that goes through the normal surface at the point of impact, right? So you can see it passes through the center of each of these, right? And if you were to zoom in here, it's 90 degrees to the interface of the two particles, right? When we talk about something that's a central impact, we are talking about when the mass centers of the two bodies lie on the line of impact. Okay. And when we're talking about an oblique impact, it's when they come in at an angle. Right. So if two things come in head to head, that's a central impact, right? If two things are angled, that's an oblique impact, right? So direct central impacts, we can have a couple of things happen here, right? We're going to talk about this in stages, right? So in the pre-impact stage, right? Ball A is chasing ball B. And ball A is going to catch up, right? So the rear one's moving faster than the front one. Upon impact, the bodies undergo a period of deformation, right? If you've ever watched slow motion video of a football being kicked or a golf ball being hit or a turkey going through a plate glass window, right? Mythbusters. Oh, I don't know if you guys seen it. That's a good one. If you haven't seen that one, definitely check that out this weekend, right? But if you ever watch a slow motion video of two things colliding, you will see they will hit, and then both objects will deform a little bit, right? Because there's some energy that is being given off by each. What happens next is we call the period of restitution, right? So after they deform, they're going to bounce back to their original shape in most cases, right? In a perfect world, everything would bounce back to its original shape, right? They either regain their shape or they remain permanently deformed, one or the other. We want to determine the velocity of two bodies, so the total momentum of the two-body system is preserved. All right, so notice we're saying here the total mass of ball A at the initial stage plus the velocity mass of B plus the velocity of B initially is equal to this here, right? That should be VA prime, not VB prime. That's very confusing and incorrect. Let's get rid of that. What is this saying? This is saying the total momentum of our two-particle system at the beginning has to be equal to the total momentum of our two-particle system at the end. Well, Dr. D, what happened to the impulses, right? Because you said that we need to have impulses. Yes, I did say that, right? But when these two things collide, don't they just have the same impulse on each other in equal yet opposite directions? So when you have a collision of two objects, the force at which ball A is hitting ball B is the same as the force of ball B hitting ball A, just in the opposite direction, right? So the impulses cancel, right? Because you have positive F and negative F. So the net effect of that is no impulse, and so momentum is conserved in these collisions. In order for us to figure this out, though, we're going to need another equation, okay? So where does that come from? Okay. There's our impulse momentum equation, right? So this is during deformation. So we have our initial impact, the ball's hit, right? P is the force of deformation. You can see this one's a little bit deformed, but it's flat there. Then we have the period of restitution. During the period of restitution, the velocity of our ball has changed to what we call U, right? It's an intermediate variable that we're using there. We're going to call it U. Right, when we get here, right, this is the starting point of restitution is the ending phase of deformation, right? Plus the impulse due to us reforming our object is equal to my final momentum of my particle, right? That's what it equals. So if I take this equation, which is equal to MAU, right? And I plug that into here, right? And I do some algebra, I'll get something that looks like this, which is the ratio of my restitution to my deformation, which we call the coefficient of restitution. And coefficient of restitution ranges between 0 and 1. And what it tells you is essentially how much energy is being transferred in this system during an impact. You can do a similar analysis on particle B, right? Because we cut the system in half, right? We're just talking about particle A. You can do the same thing for particle B. Look, you get something that's very similar here, right? It's flipped though. So what do we do with that? Well, we're going to solve for U, and we're going to set them equal to each other, and we're going to algebra, and this is the equation that you all really want to write down right here. This guy, right? Notice, what's VB minus VA? VB prime minus VA prime. That's the same as our relative velocity of B with respect to A in the final position. Right? So this is saying that the final velocity of ball B minus the final velocity of ball A is equal to the coefficient of restitution times the velocity of A minus the velocity of B at the beginning. Okay? Or you can rewrite it in terms of E and solve for what your coefficient of restitution is, right? We can talk about something called a perfectly plastic impact, right? I don't normally like to call it perfectly plastic impact. I will typically call it an elastic or a perfectly inelastic impact, right? Inelastic impact. What is a perfectly plastic impact? Well, when E is 0, what happens? When E is 0, there's no restitution. If there's no restitution, the things stay deformed. If they stay deformed, imagine a really bad high-speed car accident, right? Imagine a really bad high-speed car accident where these two cars are then so deformed that they become like one mass of metal together, right? That's what we're talking about. These two things have moved, they've exerted so much energy into deformation that they will not be separated. So they have now become one thing, right? So the final velocity of B is equal to the final velocity of A is the total final velocity. So when we have something that's perfectly plastic or perfectly inelastic, right, it doesn't bounce back. It deforms, and those two things are then traveling at the same speed after collision. This is a very real world thing that can happen, right? It's horrible when it happens, but it's something that can happen. What about like a crash test? If you ran a crash test car into a wall, right? That's perfectly plastic, right? Because at the very end, we have stopped moving. And both of those objects that collided have the same velocity, which is 0. We can talk about the other end of this, which is something that's perfectly elastic, which is not at all realistic whatsoever in any way, shape, or form. You will never see, if somebody tells you that, hey, I did my calculations and I got a coefficient of restitution of 1, you should back away slowly, right, and just go. They're clearly a psychopath, right? Either that or they're being held hostage and they're trying to tell you. It's one of those two things. Okay. So what is it, right? So the total energy and momentum is conserved. So the total velocity before, or the difference in velocity before is equal to this difference in velocity after. You can get up pretty high. What would this, something that's close to 1, what would it look like? Low speed car crash, right? Little fender bender. You hit at like 5 miles an hour and both cars bounce away, right? Sometimes you get a little bit of damage. So it's close to 1, but it's not actually 1, right? Because 1 means that everything is preserved completely, right? There's no damage on those cars whatsoever. And that's never the case, right? There's always a little bit. Some of your energy is transferred into heat, right? Some of your energy, it's not completely mechanical all the time. So this is the spectrum, right? So the closer we are to 1, the more likely we are to bounce away from each other, right? So the higher the coefficient of restitution, the more likely that impact will bounce. The closer to 0, the more likely they are to stay together after impact. Nick.
So in the equation you have square emphasizing the ring loss.
Yeah.
So the other one deals with mass. So does that equation only apply if mass is in it, or does it get anything else?
No, they're regardless of what the masses are, because of the way it's derived. Remember, we started from this equation and this equation, where we were able to get down to here first because the masses for A are the same throughout, right?
Okay.
And then in this equation, doing a similar thing for particle B, we're able to eliminate the masses of B.
Okay, so no matter what the masses are, two moving on to each other, you use that equation.
Yeah.
Okay.
So yeah, this is something that is true regardless of what the masses of the two objects that are colliding are, right? And it's pretty powerful because of that. It's pretty powerful because of that. In the real world, when I was working in accident reconstruction, this is something that we would do all the time, right? We did everything by momentum, energy, and restitution methods. Yeah, you could, so Newton's cradle would be close to 1, right? It's not exactly 1, because remember, this is saying, it says total energy is conserved, right? And in the real world, you're losing energy in Newton's cradle due to sound when they hit, and also slight friction, like through the air, right? So sounds weird to say, but wind resistance for Newton's cradle, right, is what eats its lunch. One really implies that, like in the case of a Newton's cradle situation, that your Newton's cradle will never ever stop, right? Never stop moving, because all of the energy is completely transferred every single time there's a collision, which is not, because we live in the universe where the second law of thermodynamics prevails.
So you basically, so I guess I got that in from the restitution on that, right? It's like unit per E.
Unitless. There's no units for E. It's just, think of it as like a scaling factor, right? So if it's 1, then you didn't lose any velocity, right? If it's low, it means that it's going to change in some way, right? So think of it this way, right? This is the relative velocity of my ball B with respect to A, right? So how is B moving with respect to A at the end? And we're comparing that to how A moves with respect to B at the beginning, okay? And so what this is telling us, what E is telling us, right, is either that velocity, right, if it's 0, if E is 0, that's telling us what? Well, this goes away, telling us that the final velocities are equal, right? It's telling us that the two particles are moving at the same speed at the end, right? If it's 1, this is telling us that we haven't lost any of our total velocity in the system. It's all still there. It might have shifted between, so think of like a pool ball, right? Think of a pool ball. If they were perfectly elastic, right? If they were perfectly elastic, you would be able to transfer all of the energy from the cue ball, get it to stop, and have whatever ball you're aiming at, let's call it the 2 ball, moving at the same speed that you had for the cue ball before they hit, right? That's what it's kind of telling us. Right, but there's no units on it. It's just a scaling factor. It's really a measure of how much energy is transferred in our system. Any other questions? And what about oblique central impacts, right? Can we have an oblique central impact? Yeah. So how do we deal with this? It's a little trickier. Right? Two things hitting head on is fairly easy to deal with. But if they're angled, we're gonna have to do a trick. So if they're angled, we're gonna want to talk about this in terms of tangential and normal components, right? Because remember, what is a central impact? It's one that happens along the line of impact, right? Where the mass centers are along the line of impact. And that means that if our line of impact is here, this is a normal to both of these balls, right? So we can have a normal and a tangential coordinate system here. And turns out that the tangential component of momentum for each particle is conserved, right? So it turns out that the velocity of A in the tangential direction is equal the final velocity of A in the tangential direction. So there's no change in the tangential direction here. There's no change in initial or final momentum. So we know that VA has to equal VA prime and VB has to equal VB prime in that tangential direction, right? But what happens in the normal direction? Well, the normal components of the total momentum of the two particles is also conserved. But in this case, they are a function of each other, right? So how much do they change, right? So we can rewrite that like this, right? So we can write our coefficient of restitution in terms of the normal components of our velocity, and that will allow us to solve this equation. Same rules apply here, right? If E is 0, then VB prime is equal to VA prime in the normal direction, right? And if it's 1, then we've transferred all of our energy seamlessly. Okay. You guys have any questions on this? This is for oblique. So think of it this way, right? They're hitting at an angle. And because they're angled to one another, we're going to, instead of using an XY coordinate system, we're going to say, well, I know that this surface is normal, and I know that anything that moves perpendicular to that's going to be tangential, right? And so we can describe this in the motion in this plane and the motion in this plane. So likely what will happen, right, what would you expect? These two things will hit. This will likely bounce this way, and that one will likely bounce that way, right? Likely. Depends a lot on what the momentum, what the mass is of each object and how fast they're going.
So I was wondering, why do they show that at an angle in the part? They don't show any like vertical.
So why do they show it tilted instead of flat? Is that what
Yeah, I think it's.
I mean, we could rotate it, right? It would be the same, right? It's less. I think they show it at an angle for highlighting the purposes of using normal and tangential as opposed to XY, right? But really, it's all about the momentum, how the momentum vectors are pointed, right? So if you rotated this until it was, you know, in an XY position, right, you'd have the same, be the same deal, right? You could rotate this potentially down this way. The momentum vectors would still be at the same angle to each other. They'd still be an oblique impact. But it's to highlight the process of using a normal tangential coordinate system, right? Because you can't always guarantee that you're going to be lined up with Cartesian coordinates, right? Can't. All right. You guys have any other questions? So the plan for this thing, just so you guys know, is I'm going to 3D print a fist on here, and I can fist bump you guys. That's what I'm going for. The problem is then I have to sanitize it somehow after every fist bump. So I'm thinking of getting some like that barber fluid, the blue stuff that they put the combs in. I'll just like leave it in a jar up here. Right? Probably work. All right. All right, so this thing, what is this thing? This is, why would you do this? Well, okay, so when the Empire was testing the first Death Star, they made a scale model and they launched the entire Death Star at the Jawa Sandcrawler. Okay, this is what this is happening here, all right? You know what I'm talking about. All right. So this is a block constrained to move along a horizontal surface, right? This thing can move on the ground, right? But it can't, we're gonna assume that it doesn't move off of the ground, right? So it's got some initial velocity v sub a, it's got some final velocity v prime of a. This ball, the mini Death Star, right, is hurtling down at this sand crawler, and it's going to strike at this angle, right? It's going to have initial velocity be here, and it's going to bounce off, right, and be VB prime there. Notice this is an oblique central impact, right? So we're talking about it in terms of normal and tangential coordinates along the surface here, right? So what do we do, right? So the impulses here, the impulses from the internal forces, F and negative F, right? We talked about this. There's going to be some force of the sand crawler pushing on the mini Death Star, but the mini Death Star is also hitting that with the same exact force, but in the opposite direction, right? So my internal forces are going to cancel. They're going to cancel. So momentum is still going to be conserved here, right? So the final velocity of the ball, unknown in direction and magnitude. So we need three equations. We need three equations here. All right, so what three equations are we going to look at? Well, let's break this down. Right? It's an oblique central impact, right? With this oblique central impact here, what happens? Well, let's draw our impulse momentum diagram, right? It's right up here. I've got the initial momentum of A and the initial momentum of B. I've got my impulses, right? I've got F delta T, negative F delta T, and F external, right? So they don't all cancel, but the between the ball and the sand crawler, they cancel, right? But there's some force from the ground pushing up, right? There's some normal force that we're going to call F external. This is going to be equal to the final momentum of each of my objects, right? So remember, from 2 slides ago, the tangential momentum of each particle is conserved, right? So we know the final tangential component of the velocity of B. We know that the total horizontal momentum of the block and ball is conserved, right? So in this case, instead of talking about this in the normal direction for the block, we talk about it in the x direction, right? Why? Well, we know that, again, this is a vector equation, right? MAVA is going in the x direction in order to discuss the complementary, in order to discuss the momentum as an apples to apples thing, right? Because it's a vector, you need to have it moving in the same direction, right? So that, for that reason, we're talking about the velocity of B in the x direction, okay? Instead of the normal. Finally, we can use our coefficient of restitution, right? But that's back at normal, right? Why? What's going on? Does that even help us? Well, look. 1, 2. Right? Does it even help us? Or remember, we should be able to figure out what that angle is, right? For VB. Right? We should be able to figure out how big of an angle we have that's shifting our coordinate system from x to normal, right? We'll have to know that. Okay. So likely you know what the angle is on the front of that, the wedge, right? The front of the wedge has some angle, you know it. That's going to tell you how you can break down the x and y components into the normal component, right? Okay. So that's oblique central impacts. So what's the takeaway for oblique central impacts, right? Basically, you can break this down however you want, right? Typically, we use normal and tangential because we know that in the tangential direction, momentum is conserved, and that's a big help for us. Also, we don't always need to use normal. We can break this down to x, but remember, that's just a trig substitution, right? Because this is, let me draw this somewhere that's unencumbered. So if this is my normal direction, right? I've got some mv normal, right? I can break that into mvy and mvx, right? As long as I know one of those angles. Will you know one of those angles? Well, you'll probably be given that angle, right? You have to be given one of these. None of these problems are magic, right? You have to be given enough information to solve them. It's very tempting to think that the book wouldn't give you enough information to solve them, but the book will always give you enough information to solve them, right? So just remember, you have to be told something, right? You have to be told something to solve it if they want a number answer. Questions? Anybody? We'll watch a video. I hope the video is next, otherwise I'm gonna look foolish. Video? Oh, not time for the video. I apologize. Now I look foolish. Who would have thought wearing a face shield and a mask, that would have happened? This is quite a stylish look, right? So can we talk about problems involving multiple principles, right? I said this at the end of last class. No thing in the real world is ever just one thing, right? So how can we combine what we know about all the different things in our toolbox, right? About Newton's law, work and energy, and impulse and momentum into a single problem, right? Can we do that? We sure can. All right, so imagine I have a simplified Newton's cradle here, right? I'm going to pull the first ball up, right? I can use conservation of energy to solve this first part here, right? Because why? Well, I know the potential energy here, I know the kinetic energy, and I know all of that kinetic energy, all that potential energy is going to be transferred into potential energy right before impact, right? So I can figure out VA2, okay? From here, I can use impact and impulse and momentum, right? Because now this is a collision. So right after, we know right before collision, and I can figure out everything right after collision, right? This ball is still going to have some momentum coming through here, so it transfers back to conservation of energy. Right? Transfers back to conservation of energy. So we can chain a bunch of these things together. Right, so let's work through this one then. So is this an oblique impact or is this a direct impact? Direct or oblique? What do you guys think? It's oblique, right? Why? It's angled. Yeah. So I'm going to throw this ball against this frictionless vertical wall. Like all good walls, it's frictionless. So this frictionless vertical wall. Immediately before the ball strikes the wall, its velocity has a magnitude of v and forms an angle of 30 degrees with the wall. If I know that the coefficient of restitution is 0.9, I want to determine the magnitude and the direction of the velocity of the ball as it rebounds from the wall. Right, so I don't know if you guys ever played this game when you were kids, right? You throw the ball against the wall, and then it's in a big group, and you have to catch it. And if the person doesn't catch it, they have to run to the wall, tag the wall, right? Yeah. Yeah. So this is that. This is the calculation that you were all doing in your head, right, at that time. Okay, you just didn't know you were doing it. Okay, so how do we do this, right? Well, this is already broken into tangential and normal components for us, right? They've already broken this down for us. All right. Coefficient of restitution of 0.9. What do you guys expect to be the outcome of this? We're going to have a large bounce away from the wall, or is it just going to die at the wall? Coefficient of restitution is 0.9. Is that going to get us a large bounce or a small bounce off the wall? What's the difference? Large bounce or small bounce? What do we think? I mean, 50-50 is a pretty good shot. It's better than SATs, man. Large bounce? Is that what I heard?
Yep.
That's exactly right, right? Why? Because it's close to 1. 1 means that it's perfectly elastic, right? 0 means that it's going to hit and it's just going to stop. And both of the things are going to move at the same velocity. And since the wall is really heavy and not moving, right? It's going to be really hard for you to change the momentum of the wall with the ball, right? Be very difficult. So how do we do it? How do we do this? Right, well, let's start with our impulse momentum diagram. All right, so what do I have to start with? Well, we've got this ball, and this has some mass times velocity in the normal direction. It's got some mass times the velocity in the tangential direction. All right, and we knew what? We know that this is traveling at 30 degrees, and this is my total momentum. My coordinate system is normal tangential. What about, so that's my initial momentum. Now we can talk about my impulses, right? Well, I've got on this ball the force of the ball hitting the wall hitting the ball, but also the force of the ball hitting the wall. So they're equal and opposite. And this is going to equal my final momentum, which is going to be, call it mv prime, which will give us mv prime tangential and mv prime normal. Yeah.
The second part is when it hits the wall.
Yeah. Yeah, that's so the second state, right, is after we've already bounced off the wall, right? So think about this as just before we hit the wall, plus what happens when we hit the wall, and then we see what happens after we hit the wall, right? So it's right before impact, the impact, and then right after the impact, right? It's kind of like the 3 phases that we're looking at here. What's that?
The first phase is balance.
Right, so it's after we've hit the wall, we're going in the opposite, we're bouncing off the wall, right? Okay. So there's a couple of things we can do here. There's a couple of things that we want to do here. So let's start with some equations, right? We'll start with this first picture, right? Well, let's figure out what the normal velocity is, right? What's my normal velocity for my ball? Now, notice I haven't drawn any momentum terms for the wall, right? Why? Because it's not moving. The wall it shouldn't move. The wall's moving, there's bigger problems, right? And so the wall's not moving. So how do I figure out what this normal velocity is, right? Well, the normal velocity is just going to be V. Write that better so people can actually read it. V times cosine of 30 degrees, which is 0.866 times the velocity. Where'd that 30 degrees come from, right? Well, we can drop our vector here. But you didn't write M. Yeah, I didn't write the M, right? Why? The mass is a constant. The mass is just scaling our velocity here, right? The velocity is the vector. That is what we're drawing. Momentum is just velocity that's scaled by the mass. All right, so if we do this, we'll find that we get 0.866 V as Vn. And I can find my tangential velocity here as well as V sine 30 degrees, which is 0.5 times the velocity. Now that's important, right? Why? Because we know that in the after world here, because this is an oblique collision, we've been told that V is equal to V prime in the tangential direction. So we have this, right? Because tangential momentum is conserved. And since tangential momentum is conserved, that's what we get. We found it here. It's going to be the same in the second part, just 0.5 times V. Okay. Well, what now? Well, why don't we use coefficient of restitution? Why don't we use coefficient of restitution? Why would we want to use coefficient of restitution? Well, first of all, we know what the coefficient of restitution is, right? So it's probably helpful. Let's write down what the equation is, though, for coefficient of restitution. Coefficient of restitution tells us that the velocity tangential minus the normal prime, so in the final configuration at state 2, is equal to the coefficient of restitution times the normal velocity minus the tangential velocity. Now, I'm going to put another subscript here. Remember, when we were talking about coefficient of restitution, we were talking about the velocity of two different particles, right? Talking about the velocity of two different particles. So what we're trying to do here is figure out how we want to know in the normal direction, right? So I don't know why I wrote T there. Don't write T there. Get rid of that. Get rid of that T. That's confusing. We're going to call that V sub x. Because also, this is in normal and tangential, but it lines up, our normal force lines up, our normal direction lines up with our tangential, right? Or our normal. Normal lines up with x. There it is. Come on, Dr. D, it's Friday. Get it together. All right. Normal lines up in the x direction. So what's Vx prime? That's the velocity of the wall in the x direction or in the normal direction, however you want to think about it. What is the velocity of the wall in the x direction? It's 0. What's the velocity of the wall in the x direction at the beginning? Still 0, because it's a wall. So we can use this equation with our coefficient of restitution, and we can figure out that the normal velocity of the ball is just 0.9 times 0.866 times the velocity of the ball, which gives us negative 0.779 times the velocity. Okay, so what did we find out? From the coefficient of restitution, we found out that the normal velocity of the ball afterwards is going in the opposite direction, right? So it has changed directions, which makes sense because it's going to bounce off the wall towards us. It's going to go negative point, and it's going to scale our velocity by 0.779, right? So whatever our initial velocity was, it's about 78% of our initial velocity. So by throwing the ball off the wall, we are slowing the ball down, which makes sense, right? Because we've all thrown a ball off of a wall, and we know that that is what happens. Why? Well, sound, heat, energy are released, right? Which is why you can't get a coefficient of restitution of 1. But you can get them pretty high. Can get them pretty high. Okay, so that's all well and good, right? That's all well and good. But can we figure out, can we write a vector for our final velocity in terms of our normal and our tangential component? And the answer to that is yes. Yes, we can. All right, so I want to write the vector for V prime. And what's that? Well, that's going to be Vt times E sub t plus Vn prime, these are primes, E sub n. Well, I can plug in what I just got, right? I know V prime t, that was 0.5 times V E sub t. And I know it in the n direction, that's negative 0.779 times the velocity E sub n, that shouldn't be fine. So if I want the total magnitude of my velocity, how do I do that? Right, because I just want to know what is the velocity here. I want to know the amount of velocity, the magnitude. So I want the magnitude of V prime, right, which is the absolute value of V prime, right? And how do I do that? Well, the square root of the sum of the squares, right? We use Pythagorean theorem. Remember what this is saying. This is saying that each one of these is a leg of a triangle, right? We go in the tangential direction by 0.5. We go in the normal direction by negative 0.779, and our total is the vector between those two, right? So it's just Pythagorean theorem. And that will leave us with 0.9257 times the velocity. All right. Well, that's a thing that happened, right? So it turns out that by throwing the ball against the wall, we've retained 93% of our initial velocity, right? Which is cool, which is expected, right? Because why? Because we didn't have a coefficient of restitution of 1. It would be 1 if we had a coefficient of restitution of 1. All right, but if I have a vector, I want to talk about vectors, right? And how do we characterize a vector, right? We need a position and a magnitude, right? So this is my magnitude. And normally when we break it down into rectangular components, we talk about have this much in the x direction and this much in the y. Have this much in the normal, this much in the tangential, right? Another way of doing that is by giving the magnitude and the angle that the vector is at, right? So how do I figure out the angle of this vector? All right, so let's draw these vectors, right? I've got, this is 0.5 in the E sub t direction, right? Then if I add this, this is going to be negative 0.779 E sub n, right? And I claim, Dr. D claims that this is what we're calling V, right? This blue vector. Because that's how we add vectors, right? Tip to tail, and then we get the result. And notice this is a 90-degree angle up here. So if I wanted this angle, how would I figure it out? Which angle, right? Does it matter? No, you can define whichever one you want. Let's talk about this angle. If I talk about this angle, call it theta, right? I want to find theta. What do I know? Well, I know the normal and I know the tangential components here. If I'm looking at this angle and I want this angle, and I know both legs, that's just the tangent, right? That's the opposite over the adjacent, right? So the tangent of theta is equal to 0.5, sorry, not 0.5. What's going on here? It is 0.7, negative 0.779 times V divided by 0.5 times V, right? Because tangent of an angle is the opposite over the adjacent, right? Okay. If that's that, these V's just cancel, right? So the velocity doesn't matter. Figure this out. If I take the tan inverse of both sides, what do I get? Negative 57.31 degrees. Why? Because it's measured from the top and it comes down, right? This way. It's measured from horizontal down, right? So it's a negative angle. What if you wanted this angle instead, right? You could get that one too. You just flip it, or, I mean, since we already know theta, it's just 90. It's just 90 minus that angle, right?
So wait, is it tangent theta at 57 degrees? Is that what it would be?
No, it's where the blue one is over here. I'm saying if we wanted that green one, we could do that too. Tangent of theta is the angle from this horizontal negative 0.779 in this direction, right? That's why it's negative, because it's coming clockwise. Right? So for angles, right? Remember, we got first, second, third, and fourth quadrant. positive 90 degrees goes this way. Anything that goes the opposite way is going to be negative. In practice, you could report it as 57.31 degrees and show where the angle is, right? And that would be fine too. But just be aware that your calculator will give it to you as negative if you do it. The lower angle, right, the third angle in that triangle is just 32.7 degrees. All right. Do you have any other questions on this one? So what's the point, right? Like, is that it? Well, yeah. That's it. You know the magnitude. Depending on what the initial velocity is, you can figure out. We're never told an initial velocity, right? So what is this telling us, right? What can we get from doing this? Well, obviously, I think it's obvious, right? The velocity after collision is going to scale based off of the velocity that we put in, right? So the faster I throw the ball to start with, the faster it'll be at the end. We're still going to lose something by colliding with the wall, which makes sense. But it turns out that that angle that we're going to get off of the wall has nothing to do with the velocity. It only has to do with what? It's really just about the initial angle that you put in, right? Because that's what's going to drive how much of your velocity, that's going to drive the velocity that comes out, right? That's going to change the components that are on the backside. So it doesn't matter how fast you throw it. What matters is the angle that you hit the wall with in terms of determining what the angle coming off of the wall is. And I think that makes sense to a certain degree too, right? The flatter the angle, the more it will come back at you, right? The larger the angle, the more it'll go straight up, right? Okay. You guys have any other questions? No? No, we'll do one more, then we'll take a video break. Promise. I got a couple good ones for that. This is an interesting one, right? Because we'll see. So I've got a 30-kilogram block that I'm going to drop from a height of 2 meters onto a 10-kilogram can of a spring scale. So, like you normally do, you're going to take your 30-kilogram package, right? Like 70 pounds, right? And you're just going to drop it from about 6 feet in the air right onto the scale. Makes sense, right? Physically makes sense. All right, anyway, so we're dropping this on our scale. What do we need to figure out? We're assuming that the impact is perfectly plastic. So that's a big keyword for us. All right, what does that mean? If my collision is perfectly plastic, what does that mean for us? What does that mean? Doesn't bounce, that's right. So we can assume that since it doesn't bounce, once the 30-kilogram package hits the scale, it stays on the scale, right? And then those two things are then going to move at the same velocity post-impact. We want to find the maximum deflection of the spring, right? Knowing that the spring constant is 20 kilonewtons per meter. Okay. So there's a couple of phases, this one. There's a couple of phases. So what kind of problem is this? What toolbox? What method from our toolbox should we use? Should we use Newton's second law? Should we use impulse momentum, work energy? What should we do? What do you guys think? What do you guys think? So what are we thinking? What's happening here physically? Let's talk about that. Yeah. No. Do something for us. What's happening here physically? What's happening here physically? What are we trying to describe? What's the first thing that happens? Let's break it down into pieces. All right. So what's going on here? What's going on here? Where should we start?
Well, so I guess our first objective is to find the velocity of the spring after it's fly. So figure out the velocity of the block before I make the spring.
Yes. How would you do that?
Well, we do, yeah, I guess we do know acceleration, but so yeah, I guess if you know the height, you can take the derivative of the position involved.
I mean, you could do that, or you know that it's a certain height above something. You know that it starts from rest. And we can assume that it starts from rest because we can use work energy for the first part, right? Logan.
Does the height of the spring not matter in this situation? Like how
Mm.
long
Oh, it does, and we'll get there in a second. Good question. So yeah, the height of the spring definitely matters, right? Is it fully deflect? Is it undeflected when we start, right? Is there preload in the system? Like how do we? So yes, it matters, and that's one of the things that we'll end up having to figure out. But we got to step through this sequentially, right? So think about it, right? The first thing is this is dropping, so it's in free fall. Then it's going to collide with the scale. Then, right after collision, the spring's going to deform, right? Then the spring's going to come back up a little bit, right? So there's this little bit of give in there, right? So what? So we're going to use work and energy. This is going to use multiple different methods for us to figure out, right? Because just like that Newton's cradle example that I showed, right? The first part is work energy. The second part is going to be impulse momentum, right? We're probably going to have to use Newton's law at some point. So where do we start? We'll start here. Let's start here. There's no good place to move this, so it's going to go right here. All right, so if we start here, right, look, I've got state 1 and state 2, right? What does state 1 tell me? State 1 is the initial state, right? I've got some velocity v sub a, it's equal to 0, right? I'm dropping this. The implication of me dropping this is that I'm holding it steady before I drop it, right? You didn't throw it, you dropped it, okay? It's going to fall 2 meters. I'm going to use as my datum, I'm going to measure from the top of the scale pan, right? Both of these are not moving at the start. They are both static. So there is no kinetic energy, right? T1 is equal to 0. V1 is all due to potential energy here, right? The spring hasn't condensed yet. We're going to have all potential energy due to gravity. That plate B is not moving, and it is at the datum, so it is not shifted. in our gravitational field. So we're only having to deal with the weight of our package, which is 30 kilograms times 9.81 meters per second squared, times the height through which it drops, which is 2. So we get 588 joules. That's also mgh, right? Here's the mass I was given, here's gravity, here's the height compared to where I'm measuring from my datum. All right, looking at state 2. So what's my final energy here? Well, all of my potential energy was converted into kinetic energy, right? And we are stopping where we're looking at this a split second before these two things touch each other, right? So right before impact, right? So this V sub B is still 0 because it hasn't had enough time to develop a velocity. So V sub 2 is 0, T sub 2 is 1/2 ma VA2 squared. Or I can plug that in. I can run my conservation of energy equation. Right, so the sum of my energy, the kinetic plus the potential energy at the start is equal to the potential plus the kinetic at the end. Well, that's 588 is equal to 1/2 30 VA2 squared. We can solve this for VA2 at 6.26 meters per second, right? So problem like this, right, we need to break it into positions, right? So we've got the drop. So now we've characterized the drop. And the thing that's important about this is we found the velocity of our crate just before impact. So the next thing we're going to do is we're going to talk about the collision. That's the next thing we're going to do is we're going to talk about the collision because again, think about it as we dropped it, we're watching the video of it and we freeze it at the exact perfect moment that these two things are just about to collide, right? And that's where we've calculated this velocity. Are we okay with, we're okay with this conservation of energy? We're good with why we would want to use conservation of energy here. I know I said we'd go over keywords and phrases, right? You were given a height and you were given the initial velocity, and we know that we have to find the velocity prior to the impact, right? If you're given velocities and heights, right, they play really well into you using potential and kinetic energy.
And the 6.26, is that
So it's 6.26 meters per second. Is that what your question was there?
yeah,
Oh no, not V of M, that's VA2. I mean, I think that one is like pretty obvious. It's not. My handwriting is horrible. I apologize. I feel like I'm going to be apologizing for that a lot. Just call me out on it. It's fine. Okay. So VA2, right? That is the velocity of block A at state 2. That is the velocity of our block right before impact, right? So how do we take this to the next step, right? Because eventually we want to see how much does this spring deflect, right? That's what we want. So how do we go about this? Well, good question. State 2 plays into state 3. So right before impact to right after impact. Remember, they told us in the problem statement that this was what? Perfectly If it's perfectly plastic, that means the coefficient of restitution is 0. If the coefficient of restitution is 0, that means that everything that's touching up there is moving at the same velocity after the impact, right? Which is why we only have V3 drawn on our diagram. So I can use conservation of momentum here. Why don't I have an impulsive force? Right? Well, we talked about that. I don't have an impulsive force because they're canceling each other out here, right? The force of the block hitting the scale is the same as the force of the scale hitting the block. They're equal and they're opposite. They're going to cancel. So we don't have to worry about that. We have conservation of momentum, right? So MAVA2 plus MBVB2, right? But VB2 we know is 0 because it's right before impact. And that's going to equal the total combined mass of the crate and the scale times the velocity at 30, right? Why is it? Well, think about it this way, right? They hit and they're both moving together, right? So now these two things are one thing. So we have to combine their mass for a total mass. We were told what the mass of the scale was. And we were told what the mass of the scale was. We can plug all of these things in and we can find that the velocity of the block and the scale together right after impact is 4.7 meters per second. Now, does that make sense? Would you have expected it to be less or more after impact? Would you expected that velocity to be less or more after impact? Less, right? Why? Because it's heavier. It's heavier, right? And so if the momentum hasn't changed and you've increased the mass of the system, then the velocity has to decrease, right? Right. So then what? Well, then we can chain this back into energy again. And this is going to be fun, right? So there's some initial, we're going to define this, X3. Right? X3 is going to be that initial spring deflection that Logan was asking about, right? There's some initial, because this pan has some mass to it, right? That spring is going to deflect a little bit to start. We call that X3, right? What do we know? Well, we know that the force is equal to the spring constant times the distance that is moved. We can rearrange this to find X3, right? Where X3 is just the weight of the pan divided by the spring constant, okay? Right? So if we use Hooke's law here, right? Wish I had a spring right now, right? But imagine I hung a spring from the ceiling and I put a 2 kilogram mass on it, right? It would extend. There would be some preload in that spring, yes? Right? Maybe? Who knows? Right? You would expect some preload to be in that spring if I hung something off of it, right? And just let it sit there. Same deal here, right? That top of that scale has a 10 kilogram mass associated with it. It's a strong spring, but it's going to compress it ever so slightly, right? How do we figure out what that initial compression of that spring is? Well, we use Hooke's law, right? Well, the force is equal to K times X. I rearrange this, I can solve for X using the weight of my pan. It's 10 times 9.81 divided by 20 times 10 to the third, right? Because there's a 20 kilonewton per meter spring constant. I just converted it to newtons. And you find out that that spring has deflected initially by 4.91 times 10 to the minus third meters. Some people call that millimeters, you know, some people. So we've moved by like 5 millimeters, right? So a 10 kilogram mass moves this spring by about 5 millimeters. So we have 5 millimeters of travel in this already without us even doing anything to it, before we even drop anything, right? Okay. Why is that important? Well, if I set my datum to where this was right at the end of state 3, right, it's not going to be the same as x3. And I know it's confusing because I called it x3. It has literally nothing to do with state 3. That is the initial spring deflection. You know, if it makes it, we can make it less confusing maybe, right? Let's call this delta, right? There's some change in the height due to that scale having some mass to begin with, right? I'll change it in all of its permutations here. Why is that important? Why is it important to take this into account? Is it important to take it into account?
So the formulas for how far the spring presses after it.
Yeah.
So it's like 4.91 millimeters down.
Exactly, right? So there's that reason, right? We want to know how much after the collision we've moved, and this is already at that level pre-collision. The second reason is it's going to affect our spring energy, right? Because now we're not moving from the undeflected position. We already have some energy that is stored in there to begin with. Right? We already have some energy stored in there to begin with. So we can look at our kinetic energy at the instant right after impact, right? For state 3, how much kinetic energy do I have? We're going to assume we have no potential energy because we're going to track everything from starting from state 3. So what is the change from state 3? And in that case, we've got 1/2 ma plus mb times v3 squared. We know all of those things. We plug them in, we calculate. We've got 442 joules of energy, kinetic energy. What about V at state 3? Well, V at state 3 is just the gravitational plus the elastic, right? And like we just talked about, at state 3, because we have that delta in our spring already, we've got some energy stored in there. How much? A very, very, very tiny amount of energy. Significant, almost a quarter of a joule. Is that going to make or break our calculations in the real world? Probably not. However, what if you didn't have such a strong spring in there, right? So we do need to take it into account. Turns out it's fairly negligible in this case, right? But it's there nonetheless. Okay. So we've got all of our energy for state 3. We can do the same thing for state 4, right? So if you're looking at state 4, what we're trying to solve for here is h, right? Because we know we've moved some total distance x4. We know that this was preloaded by delta, right? But h is the distance from the datum to where I moved now. Okay. You guys have any questions so far? I feel like the question's going to come up with how are we supposed to know to chain all these things together? I feel like that's going to come up. Well, one is practice, right? But secondly is this, right? If you think about it in a step-by-step method, right? You know, we'll go through the rest of it and then we'll talk about it. How about that? I think that'll be a better idea. So we don't get derailed from doing this. You guys okay so far here? Yeah? So we're just going to calculate our energy for state 4, right? If we calculate our energy for state 4, we have gravitational and elastic energy, right? Our spring has moved by some distance. We have moved our block by some distance, right? By negative h. And so we can plug these things in. We know the weights of A and B, right? I changed h to x4 minus x3, right? Because I want to know the total distance that everything has moved, not the distance based off of what my preload is, right? And so I have that. And what's my kinetic energy at the end, at 4? Well, we're going to assume that the kinetic energy is 0. We're going to say, well, it's not really an assumption. We've dropped this onto the scale. The scale, it impacts the scale, it pushes it down, and our final snapshot of this is it's just sitting there, right? It's at rest at the end. So everything has come to a rest. T4 is 0. V4 is just my gravitational minus my elastic, or plus, that should be plus my elastic energy for state 4. For state 4. Right. We know T3, we know V3, we know T4, we know V4. Right. We know X3, we just have to solve for X4. Right. And if I solve everything for X4, I get 0.23 meters. But remember, we wanted the distance that it's traveled, right? We want H. Why do we want H? Because it takes into account our preload. So we know how much it's actually moved since it started. Yeah.
Why is it weight A minus weight B?
Probably because when I copy pasted it, it was a true copy pasta and it changed it. Apologize. Yeah. So just so you guys know, not that it affects your daily lives whatsoever, but if you try to copy and paste things that you've written on these slides, it doesn't always grab all of the marks all the time, and it makes for some really poorly timed signs. It will often make positive or plus sign. It often turns addition into subtraction. Right? Like this one. This one should be plus 2. Right. Now I guarantee that this problem, all the problems today, have been free of math errors, unlike last class. Today, one time only, free of math errors. I promise. All right. Okay, so we find X4, right? Let's go back a slide for a second, right? What is X4? Remember, X4 is the total distance that we've traveled, right? The total distance, right? What we want is H. We want to know how much the spring has changed, right? But why? So why? Why not convert something else? Why not convert X4 into H? I mean, you could have converted X4 into H up here and done that, but then you'd have an H squared, right? And you'd have to do a bunch of other stuff. This doesn't really matter. 6 of one, half dozen of the other. This is the way I decided to do it. So I've got 0.23 meters, and then to find H, which is the height that I have moved, it's X4 minus X3. It's 0.225 meters. Okay. So let's answer the question. How are you supposed to know how to do all these things together, right? What was asked? We were asked to find how far this moved after the collision, right? That was the main question. So you know that you're going to have to do a collision at some point, right? Because these things are going to collide. So you write out your equations for the collision, right? Which is the middle step. Okay? Because you know it's a collision. So you know that there's going to be momentum in there somewhere. And you're told what the coefficient of restitution is. So you should be able to figure it out, right? But then when you do that, you're going to notice, well, I don't know VA2. How do I figure out what the velocity is prior to impact? Well, I need to use work energy, right? That makes the most sense. Figure out what work energy tells me to solve for VA2. Where do I go after that? Well, that's going to cause a height change in the spring. And I can't deal with that with impact momentum, right? Because impulse and momentum only gives me velocities in time. And Newton's law isn't going to tell me anything about the height change. So we're back to conservation of energy. Sometimes it's helpful, right, to start with what you know. You don't always have to do it sequentially. right? Start with what you know is happening and go from there. However, I will say most of these things, like keywords, right? So if you're given a force and asked for an acceleration, you're probably doing a Newton's law problem, right? If you see the word collision, automatically go right to impulse and momentum. Do not pass go, do not collect $200, right? Just impulse momentum all the way for collisions. If you're ever asked to find the amount of time and given a force, also impulse momentum, right? If you're given a displacement and asked for a velocity, or you're given a force and asked for a displacement, work energy. I have a flow chart. We'll talk about it in another class. It'll keep coming up because here's the way that the class is structured, right? We're going to go over all this stuff for particles, okay? Then we're going to go over it all again for rigid bodies. So this is not going to be the last time that we talk about these things, right? But for particles, right? That's everything that's going to be on the first let's call it the first quest, because it's not really a quiz and it's not really a test, right? Some combination of the two. So everything that's on the first thing, the first quiz test quest, is all particles, right? It's everything to do with particles. Our first quiz is 2 weeks from today, right? It's 2 weeks from today. It's not worth a huge amount of points. It's worth like 35 total points or something like that. Okay. We'll talk more about it next week. Okay, for sure. You guys have any questions here? Comments, concerns? That's a long problem, right? I had everything written out, and that one still took us quite a bit of time, right? That's a long problem. As we move on through the semester, some of these were, especially when we get to rigid bodies, right? Some of those problems, they take time, right? So just be sure that you're aware of that when you're going into the homeworks, right? You're gonna need some time. Marcia, so.
Don't show us. Please don't show us. But what is like the longest problem you've ever done?
Ooh.
I agree with that statement. Don't show us.
So my other class, I just recently did a double pendulum with a mass in between the two of them. That's pretty beefy. In grad school, I had a professor for our dynamics class. We had to derive everything for any system that he gave us from scratch. No pre-canned equations or anything. And those were all really, really long problems. Like those would take, like we would get take-home exams. It'd be 3 problems. It would take you the whole week to suss through them. So they can get pretty hairy. I had another professor for a controls class, which is not, it's related to dynamics, right? But it's not the same. He would routinely give us 20th order systems to work on, which are by hand, which is a pain in the butt. So they can get pretty crazy. Some of them. The one that I'm thinking of seemed pretty simple to start with. It was kind of like it was basically, I don't know what the device was, but it was essentially the size of a dry erase marker that had a weight inside that had a spring on either side, and you were throwing it, so it was rotating, and you had to determine what the angle was going to be when it hit the ground and how much energy, like how high it would get off the first bounce. That took a long time. And I don't really feel like it had any real world application. So it was like, why am I doing this? Yeah, why is there a spring inside of this pen with a weight in there? Yeah, I guess like old school grenade, like old school German grenade, right? Funny story. Well, I guess depending. Funny like weird, not funny like haha. Let's go with that. You guys know why the U.S. Army switched the shape of their grenades, right? From the stick ones to the ones we have today. Because we played so much baseball is our pastime. Other nations didn't play as much baseball and they weren't used to the shape. And so it was harder for them to pick them up and throw them back. That was the idea. Random knowledge, right? All right, anyway. Any other questions on this, right? No? Well, in that case, let's watch a video. We'll watch some videos on impact. Excuse me. Don't be rude. Give me 1 sec. Nope, sharing computer screen. Yeah. Okay, all right. Oh, this is gonna be loud now.
It's one of the most explosive hits in all of sports. The collision between a driver and a golf ball that produces more than 3/4 of a ton of force.
There's definitely times when you know you hit it perfect, especially when it just feels great.
Mike Miller is a professional golfer who won the Wilson Cup Invitational in 2013 and is a 2-time Metropolitan Golf Association Player of the Year.
I find it that I'm able to drive the ball relatively straight and long just because of the confidence that I have with my driver.
Miller's drive is a good way to illustrate 2 key physics concepts, collisions and compressions. A collision happens when 2 objects come into contact with one another, in this case, when the club head strikes the ball. Compression occurs in the 500 microseconds that the driver is in contact with the ball, an impact that causes the ball and the club head to compress, especially the ball that deforms like a coiled spring.
When the driver hits the golf ball, there could be 2,000 or 3,000 pounds of force between the two. When you put 3,000 pounds of force on a golf ball, it can only do one thing, and that's deform.
Unlike kinetic energy, the energy of movement, potential energy is the energy an object possesses due to its position or configuration. The ball's compression produces elastic potential energy because of the way it compresses just before springing back.
The golf shot is very dependent on the storage of energy in the golf ball during that impact.
During impact, the ball deforms and stores some of the kinetic energy of the club as elastic potential energy in the ball. Because the ball's elastic energy is converted back into kinetic energy, the ball flies off the club.
Golf balls tend to lose energy in the process, and in general they lose about 40% of the energy that you put into them.
Since it takes fractions of a second for the ball to deform and come back to its former shape after being hit, the USGA uses a machine called the Universal Tester that can put varying amounts of force on a golf ball to help examine how it compresses when it's struck.
This machine will, in a controlled way, load the golf ball up to 2,000 pounds and then let it restore to its original shape.
To find out how much energy is transferred between 2 objects during a collision, scientists can calculate the coefficient of restitution, or COR. This is done by measuring the difference in the speeds of the 2 objects after their collision and dividing the difference between the 2 speeds of the objects before their collision. The answer will be expressed on a scale between 0, meaning the minimum of energy was transferred, and 1.0, meaning all the energy was transferred.
If 2 objects approach each other at 100 meters per second, and they collide, and then they separate at 80 meters per second, then the coefficient of restitution would be 80 divided by 100, or 0.8.
If a golf club can store more energy in the club head during a collision, less energy is lost, creating greater ball speed. Manufacturers work hard to develop club heads with greater flexibility. To ensure the game does not rely only on technology opposed to a player's abilities, the USGA puts limits on the performance of golf equipment.
This is the pendulum test. It's got one purpose, and that's to find out how flexible the club head is.
In the pendulum test, a steel ball attached to a hammer swings into the club face. The acceleration of the steel ball into the club face is measured, as well as how long the impact between the ball and the club face lasts.
If it was hitting something rigid, it would bounce off very quickly, and if it was hitting something flexible, it would kind of catch it and release it quite slowly. And we've got some nice electronics that can measure that down to this less than a millionth of a second, measure that timing, and we put a limit on that time, and that limits how flexible the club head can be.
Even with the limits placed on technology, today's golf equipment still provides plenty of ways to improve a player's game.
You got to go out there with the attitude of it's a new day and it's a new experience. That's why it's golf, and that's why it's phenomenal.
With the right practice and skill, golfers like Mike Miller can use a club to put compressions and collisions to their advantage, leading to success on the course.
We'll watch one more. Solid. All right. We'll start this up. We got a few more minutes. Run down here. Like 5 minutes. 5-10 minutes early today. See. Probably not. We'll see how it goes. All right. So topic 3, right? So all that stuff. Topic 2, right? Topic 2 went over what? Topic 2 went over Newton's second law, work, energy, and impulse momentum, right? Okay. So what happens if we have a system of particles? So why even talk about a system of particles, right? Well, what we're going to start talking about in systems of particles is ways for us to say, well, we have a group of particles that's all moving together, right? Think like a cloud, right? A cloud is a system of particles, right? If I blow that cloud with a fan, all of the particles are moving. Now, for our illustrative purposes, let's assume that cloud doesn't diffuse out everywhere when I hit it with the fan, right? It all stays together, right? It's the same cloud. Right? We can talk about how that cloud moves by tracking the center of gravity of the particles, okay? This is going to lead us directly into a lot of things that tie into how rigid bodies move and how we can talk about rigid body movements. But for this particular topic, we want to be able to use to solve kinetic problems using the second law and using energy and momentum methods. So again, we are going to be using Newton's second law and work energy and impulse momentum, so the tools that we just developed, but we're extending that to systems of particles, right? So more than just 2 particles interacting. How do these systems of particles work? Right? So there's a couple of things that we're going to want to talk about, right? First is that the effective force of a particle is defined as the product of its mass and acceleration, right? So, hey, that's just Newton's second law, right? Sum of my forces is mass times acceleration. It will be shown that systems of external forces acting on a system of particles is equipolar with the system of effective forces of the system. So that basically means that they're equivalent. Okay, basically means that we're going to show they're equivalent. The mass center of a system of particles will be defined, and we are going to use that to talk about the motion of a system of particles, right? So we're going to track a system of particles. Think of it as a cloud, right? A point cloud. We are going to track that cloud by the center of gravity of the cloud. Applications of work, energy principle, and impulse momentum principle to a system of particles will be described. We're going to talk about the results obtained that are also applicable to rigid bodies, which is where we're going after this, right? And analysis methods will be presented for variable systems of particles. So we're going to talk a little bit about fluid mechanics. Just a little bit. Then we're not going to do anything else with it really the rest of the whole semester. We're going to stick on, I mean, you guys have a whole class on fluids that you're going to take next year, right? Okay. Anyway. Engineers often need to analyze the dynamics of systems of particles. This is the basis for many fluid dynamics applications. Will also help establish principles used in rigid bodies. Okay. We have, you know what? We're just gonna call it. It's Friday. I don't feel like trying to go through the derivation of Newton's laws and momentum for particles. So we'll just call it for today. Okay, guys? I think that next class we will get into topic 3. We'll go through a couple derivations. Again, remember the point is not that you know how to derive it, it's so you've seen where it comes from, but we want the punchline and we want to know how to use this tool in our toolbox, right? Hold up. That's what I was looking for. All right. So I'll leave this up. You guys fill it out and you can go. Have a great weekend. Remember, right? I say it every weekend, right? But remember, focus up, get your stuff done that you need to get done, but also try to make sure you do something that disengages your mind, right? Don't burn yourselves out. Make sure that you're taking care of yourselves, right? A quizzer. Yeah, you don't have to worry about that. That guy, don't worry about that guy. Remember, I have office hours from 3 to 5 today. Have a good one. Take it easy. Good weekend, guys.